Have you ever wondered if everything you thought you knew about reality might be wrong? What if the way we talk about quantum physics, this mysterious mind-bending science, is hiding one of the biggest mistakes almost everyone makes? Today, we're going to uncover that mistake. And by the time you reach the end of this video, you'll see quantum physics in a way that very few people ever do. Now let me ask you this. When you hear the word quantum, what comes to mind? For most people, it's something strange, something magical. A cat that is both alive and dead. A particle that is in two places at once. A universe that changes the moment you look at it. But here's the shocking truth. Much of what you've been told is twisted. It's simplified, distorted, or even flat out wrong. And if you don't know this, you'll fall into the same trap almost everyone does. This mistake isn't just about science. It's about how you see yourself. It's about how you understand your choices, your possibilities, and the unseen forces shaping your life. Because whether you realize it or not, the way you think about quantum physics affects how you think about reality itself. And when your idea of reality is built on a misunderstanding, everything else becomes shaky too. So what exactly is this mistake? Here it is. Most people believe that observation means human consciousness changes reality. They think that just by looking at something, you collapse possibilities into one outcome. It sounds mystical, even empowering, right? But it's not true. The real science says something very different. Observation isn't about your mind. It's about measurement. It's about instruments, interactions, and the way particles respond to being probed. The collapse doesn't happen because you looked, it happens because the system was forced to reveal a result. That one misunderstanding has fueled endless myths. It's been used to sell books, movies, and even spiritual shortcuts. But the reality, the truth is far more fascinating and far more powerful. Because when you strip away the myth, what's left is even stranger than the fiction. Think about this. Quantum entanglement connects particles across space instantly, as if distance doesn't matter. Experiments prove it again and again, even when separated by vast distances. This is not magic. This is not human thought bending reality. This is the universe itself operating with rules that defy our ordinary logic. And yet, it's real. In this video, we're going to break down this mistake. We'll uncover how it began, why it keeps spreading, and what the science actually shows. More importantly, we'll explore what it means for you, your perception, your beliefs, and your connection to the world around you. Stay with me until the end. Because once you see through this illusion, you'll never look at reality the same way again. The mistake almost everyone makes with quantum physics isn't just a misunderstanding, it's a doorway. And on the other side of that doorway lies a deeper truth about who you are, what's possible, and how extraordinary this universe really is. Are you ready to step through? Before we talk about the real depth of this mistake, let's make something clear. Most people, when they first hear about quantum physics, imagine that observation means a person looks at something, and suddenly reality changes. It sounds like magic. It sounds like a superpower hidden inside the human mind. You look at a particle, and by the act of seeing it, you force it to become one thing or another. This idea has spread everywhere, through movies, books, and even motivational speeches. It has a certain drama to it. The problem is, it's not accurate. The truth is more grounded, but no less fascinating. Observation in quantum physics doesn't mean human eyes, human thoughts, or human awareness. It means measurement. And measurement is simply the interaction between a quantum system and a device that records or influences it. When particles meet detectors, lasers, or instruments, that interaction forces the system to reveal a definite outcome. It has nothing to do with a conscious mind willing it into existence. The mistake happens when people confuse the technical term observation with the ordinary meaning of the word. This confusion is easy to understand. The word itself feels personal. When scientists first described quantum mechanics, they used the term observer effect, and naturally many assumed that meant human observers. But in physics, an observer can be a machine, a camera, or even another particle. Consciousness isn't required. What's required is a system that leaves a trace, a record, a footprint of what happened. That's the essence of measurement. Yet the world outside science twisted this idea into something mystical, as if your thoughts alone bend the fabric of the universe. Think about it like this. Imagine tossing a coin in the dark, until you shine a flashlight. You don't know if it's heads or tails, but the coin already landed on something, it just wasn't revealed yet. In quantum physics, things get stranger, because the system really does exist in multiple probabilities, until it interacts with something. But that something isn't your mind. It's the act of measurement itself. The detector, the instrument, or the environment forces the system to settle. Consciousness is not the trigger, interaction is. Still the myth continues to spread. Why? Because it feels good to believe it. The idea that your awareness alone shapes the universe is comforting, empowering, and mysterious. It connects with human desires for control and meaning. But that's why it's important to separate science from story. If we mix them up, we miss the true wonder of what quantum physics is really saying. The real beauty of quantum mechanics isn't that your mind changes reality, but that reality itself is built on relationships, interactions, and probabilities. By mistaking measurement for consciousness, people miss the chance to appreciate the actual mystery, the fact that particles behave in ways that seem impossible, yet are consistent, predictable, and proven through experiments. When you understand this, you begin to see that the truth doesn't need to be mystical to be extraordinary. The science itself is already more shocking than the myth. When most people first hear about quantum physics, they usually don't hear it from a textbook or a scientist. They hear it from pop culture. Movies, novels, and even cartoons love to bring up ideas like Schrödinger's cat, spooky quantum effects, or the belief that our minds can reshape reality just by thinking. These examples stick because they're dramatic, mysterious, and easy to repeat. A story about a cat that is both alive and dead captures attention far more quickly than an explanation about probability waves and measurement. Over time, these simplified versions become what people believe quantum physics actually is. Schrödinger's cat is perhaps the most famous example. It was originally a thought experiment meant to show how strange quantum mechanics seems when applied to everyday life. In the thought experiment, a cat is placed in a box with a mechanism that can release poison depending on the state of a particle. Until the box is opened, the cat is described as both alive and dead. But here's what many miss. Schrödinger wasn't saying the cat is literally alive and dead. He was showing how absurd quantum rules sound when dragged into the macroscopic world. Pop culture, however, flipped it into a story that makes people think reality itself is waiting for them to open the box. The same thing happens with the phrase spooky action at a distance. Albert Einstein used this phrase to describe his discomfort with the idea of quantum entanglement. Entangled particles seem to communicate instantly across space, no matter how far apart they are. Movies and shows took this and turned it into instant communication, teleportation, or even evidence of some mystical hidden link between minds. The real physics is more subtle. Entanglement doesn't let you send information faster than light, but the image of particles mysteriously talking to each other across the universe is far more gripping. So that's what people remember. Mystical ideas also take root because they mix science with spirituality in a way that feels powerful. The phrase "your thoughts create your reality" is often tied to quantum mechanics in self-help books and seminars. The logic goes like this: since particles behave differently when observed, your consciousness must be the force shaping your life. This isn't what physicists mean by observation, but the idea has spread widely because it offers hope, control, and empowerment. In this version of quantum physics, you don't need a lab or equipment, you just need your mind. It sounds inspiring, but it's not what the science says. The reason these simplifications stick in people's minds is simple. They're easier to understand, easier to imagine, and easier to tell as stories. A dramatic tale with mystery always wins over a dry explanation filled with equations. Once a simple version takes hold, it gets repeated until it becomes common knowledge. Over time, the real science fades into the background, and the myth becomes the reality people think they know. And that's why pop culture has played such a huge role in shaping the way most of us think about quantum physics today. When people hear the word observation in quantum mechanics, their first thought is often about human eyes, human thoughts, or human attention. They imagine that a person looking at a particle causes it to suddenly decide what it is. This interpretation has been repeated so often that it almost feels natural to believe it. But in science, the truth is very different. Measurement has nothing to do with your mind, and everything to do with instruments, detectors, and interactions. To understand this, think about what happens in a physics experiment. A particle travels toward a detector. That detector could be a screen, a piece of film, or a modern device that records data. When the particle interacts with the detector, it leaves a trace. The wave of possibilities collapses into a definite outcome, not because a person is watching, but because the system itself was forced to choose a result by the act of measurement. It's about physical interaction, not mental attention. A post from a physics discussion online summed it up well. One of the biggest misconceptions that measurement magically collapses the wave function because a person is looking. This quote captures the heart of the misunderstanding. The collapse isn't magical, and it doesn't require a conscious observer. It's simply the point at which a quantum system interacts with something else in a way that produces information. That something else could be a machine, a sensor, or even the surrounding environment. The confusion comes from language. Scientists use the word observer, and in everyday speech, an observer is always a person. We observe sunsets. We observe conversations. So when people hear observer effect, they naturally assume it must involve a human observer. But in physics, an observer is anything that measures, records, or interferes with a quantum state. A particle detector is an observer. A camera is an observer. Even another particle can act as an observer. Human consciousness doesn't enter into the equation, yet the popular version persists. It's more exciting to believe that our awareness alone bends reality. It makes people feel like their thoughts have cosmic power. But this overlooks the real wonder of quantum mechanics. The fact that particles exist in probabilities, and that instruments can pin down a definite outcome, is already astonishing. We don't need to add the human mind to make it magical. It already. What actually happens during measurement is subtle but profound. The act of detecting a particle means the system leaves a mark that can't be erased. The particle becomes entangled with the detector, and the result is no longer uncertain. This is why experiments show clear outcomes every time. It's not about someone standing nearby, watching through their eyes. It's about the unavoidable process of interaction. So when people imagine that reality changes because they looked at it, they're holding on to a story that feels powerful but isn't grounded in science. The true picture is just as fascinating, though less personal. Instruments, not minds, bring probabilities into reality, and that distinction changes everything about how we understand the quantum world. The phrase stuck. Spooky action at a distance became a way for people to describe quantum entanglement. The phenomenon, where two particles become connected in such a way that measuring one instantly defines the state of the other, no matter how far apart they are. At the time, even Einstein couldn't accept that this was real. For him, the universe should be orderly, logical, and local. The idea that a particle here could influence another particle on the opposite side of the galaxy felt like a violation of the very structure of reality. But the decades that followed brought experiment after experiment, and each one confirmed what quantum theory predicted. Entanglement wasn't a trick or an illusion. It was measurable, repeatable, and undeniable. What Einstein once rejected as spooky is now one of the most well-established aspects of physics, and the most recent experiments push the evidence even further. At MIT, researchers carried out a groundbreaking study that tested entanglement over vast distances. They designed the experiment so carefully that there was no room for hidden variables or loopholes to explain the results away. The outcome was clear. Entanglement is real,
and it doesn't depend on whether a human being is watching or not. The particles remained connected, their states bound together instantly, across distances that should have made communication impossible by any classical means. This is where the misunderstanding often creeps. Many still think entanglement depends on observation by a conscious mind. They imagine that the particles wait in some undefined state until a person looks, but the MIT results, like many before them, show that human observation isn't required. The universe itself carries out the process. The particles don't ask for permission to interact. Their connection exists whether or not anyone is there to see it. What makes this so extraordinary is that it forces us to expand our sense of reality. Einstein's discomfort was understandable. The rules of quantum mechanics do not fit into everyday logic. Yet experiment after experiment shows that nature operates this way. The entangled state doesn't care about distance. It doesn't care about the limits of human perception. It exists as a fundamental truth of the universe. And as strange as it feels, it is now the foundation of technologies like quantum communication and quantum computing. Another common belief is that quantum mechanics somehow breaks relativity. This myth comes from the fact that entangled particles seem to connect instantly across great distances, while relativity tells us nothing can travel faster than light. To the casual observer, it looks like a contradiction, but it isn't. Entanglement doesn't transmit usable information faster than light. It reveals correlations that exist between particles, not communication in the way we usually think about it. Quantum mechanics and relativity describe different aspects of the universe, and while they don't fully merge into a single theory, yet they don't cancel each other out. The idea that quantum physics has broken Einstein's theory is a misunderstanding that keeps circulating, because it sounds dramatic. The rise of quantum computing has created another layer of myths. People are told that quantum computers will solve everything instantly. It's an idea that sells headlines and captures attention, but it's misleading. Quantum computers do not speed up every problem. They excel at certain tasks like factoring large numbers, simulating molecules, or solving specific optimization problems. But they are not universal miracle machines. Many problems remain just as hard for quantum computers as they are for classical ones. Experts have been clear, the promise is real, but it's not magic. The hype often runs ahead of the actual capabilities, and that's where the myth is born. Then there is the phrase superposition means being in two places. This is another simplification that sounds intriguing, but doesn't capture the real picture. Superposition means a system can exist in a combination of possible states until measured. For example, a particle might be described by a wave function that includes the probability of being in different positions. But that doesn't mean the particle is literally sitting in two spots at once. It means the outcome isn't defined until an interaction occurs. The image of two places at once is catchy, so it sticks in people's minds, but it hides the more subtle that quantum states represent probabilities, not multiple solid realities stacked together. These myths survive because they are easy to remember, easy to tell, and emotionally satisfying. They make quantum physics sound like a science of miracles instead of a science of rules. Yet when we peel back the myths, what remains is even more extraordinary. A framework that accurately predicts the behavior of the tiniest pieces of without breaking relativity, without promising instant solutions, and without needing to be mystical. It is simply a universe stranger than we expected, but not beyond our ability to understand. Simplicity sells. That's why the versions of quantum physics that most people carry in their minds are not the careful explanations from scientists, but the dramatic simplified stories that spread through media, memes, and popular culture. A headline that says particles exist in two places at once will grab far more attention than an article explaining probability, amplitudes, and wave functions. A meme about your thoughts collapsing the universe will be shared more times than a detailed paper on measurement theory. The simplified versions move faster, stick longer, and feel more satisfying, even though they aren't accurate. Media outlets know this. When they talk about breakthroughs in quantum research, they often frame it in ways that are exaggerated or mystical. It isn't because journalists are trying to deceive people, it's because they're trying to make a very technical subject understandable and appealing to a general audience. But in doing so, the edges are smoothed, the language is stretched, and before long, the explanation becomes more story than science. Once that story hits social media, it transforms again into short quotes, punchlines, and shareable images. Over time, the simplified story is all that survives. This is part of why so many misconceptions about quantum physics are so hard to shake. A detailed explanation requires effort. It asks people to sit with uncertainty, to accept probabilities instead of definite answers, and to wrestle with math that doesn't fit ordinary experience. That's not easy. Myths, on the other hand, are simple and dramatic. They give people a sense of clarity, even if that clarity is false. It's much easier to say consciousness collapses than it is to explain how quantum systems interact with instruments. A recent essay published in Nature highlighted this very problem. It explained that quantum physics is deeply non-intuitive, and because of this, myths spread. Our brains are wired to search for patterns, metaphors, and simple rules. But quantum mechanics refuses to be tamed by everyday logic. Its rules are abstract, mathematical, and often counter to how we expect the world to behave. That gap between expectation and reality leaves room for stories to rush in and fill the space. People turn the difficult science into something easier to digest, and that new version takes on a life of its own. The essay pointed out that even scientists sometimes fall into the trap of using dramatic language to describe results, just to make them more accessible. Over time, those explanations get picked up outside of science and retold without context. What started as a teaching tool becomes mistaken for the truth. This is how we end up with widespread belief that superposition means two places at once, or that entanglement allows faster than light communication. The actual science is richer and more subtle, but subtlety rarely goes viral. In a world where information moves faster than ever, the simple version will always spread quicker than the accurate one. That's the challenge with quantum mechanics. It's not that people don't want to know the truth, it's that the truth requires patience, effort, and a willingness to accept mystery. And in a culture that rewards quick answers, the myths keep winning the race. When we talk about measurement in quantum mechanics, there is an important idea called backaction. This term describes how the very process of measuring a system changes that system. But here's the key point. This happens not because a human being is standing there watching it with their eyes, or thinking about it with their mind. It happens because of the physical interaction between the system and the instruments being used to measure it. Instruments are not passive, they don't simply record data without touching anything. Instead, every act of measurement involves some form of disturbance, some form of exchange, whether it's light, electricity, or particles interacting with the thing we want to measure. That interaction itself changes the system in ways that are built into the mathematics of quantum mechanics. Think about how even in everyday life, when you try to check the pressure in a tire, the gauge slightly releases air. You don't intend to change the tire, but your attempt to measure what's inside alters it just a little. That's a clear analogy for backaction. In quantum mechanics, the effect is much more pronounced because systems are so small and delicate that any probe, no matter how tiny, becomes significant. When we fire photons at an electron to see where it is, the photon doesn't just look at the electron, it physically bumps into it, transfers momentum, and shifts its position. That's why the measurement is said to disturb the system. It's not mystical, it's physics. This is where so many misconceptions creep in. People often imagine that a conscious observer somehow decides the fate of the particle. But in reality, what decides it is the setup of the experiment, the nature of the tools, and the physical interaction itself. A camera, a detector, or a sensor, all of these will change the system by their very. And this is what scientists mean when they speak of backaction. The system is influenced not because it is aware of us, but because physics demands it. There are countless experiments demonstrating this. In quantum optics, for example, when a photon is measured using a detector, that photon cannot be measured again. The act of detection absorbs it, changes it, or collapses its state in a purely physical way. In superconducting qubits, which are used in quantum computers, back action from measurement devices has to be carefully managed because even the tiniest unintended disturbance can ruin the calculation. Engineers go to great lengths to reduce the back action of their instruments to preserve fragile quantum states. This is not philosophy, it's engineering and applied science. So when people say that looking at something changes it, they often mean it in a mystical sense. But the truth is far more down to earth. Measuring a quantum system changes it because measurement is a physical interaction. The instruments themselves, whether they are lasers, detectors, or amplifiers, play an active role, and that rollback action is built into the fabric of the theory. It's not about human consciousness bending reality, it's about the unavoidable consequences of probing nature at its smallest scales. Being wrong often feels uncomfortable, but in science it is one of the best opportunities to grow. Many of the greatest breakthroughs in physics began with misunderstandings, paradoxes, or results that seemed impossible. Quantum mechanics itself was born this way. When early physicists tried to describe how light and matter behave, their predictions didn't match reality. That failure pushed them to rethink everything, and out of that came one of the most powerful theories we have today. Mistakes are not dead ends, they are signposts pointing to deeper truths waiting to be uncovered. In the case of quantum mechanics, the common mistakes people make, confusing observation with human consciousness, thinking particles act magically, or assuming superposition, means a particle is literally in two places at once, actually open the door to learning. Each time we confront what is wrong, we refine our understanding of what is right. That is how science protects itself from drifting into myth. Instead of dismissing errors, physicists use them to clarify language and improve experiments, so the true meaning of quantum effects comes into focus. The real phenomena at the heart of quantum mechanics are already more fascinating than the myths. Take entanglement for example. Two particles can become linked so that their properties remain correlated even if they are separated by vast distances. Measure one particle, and the other's outcome is immediately related, no matter how far apart they are. Albert Einstein called this spooky action at a distance, and for years, even he doubted it could be real. Yet modern experiments have confirmed it repeatedly, closing loopholes and proving that the universe truly behaves this way. What's important is that entanglement doesn't mean magic or human thought waves traveling across space. It is a physical reality that emerges from the mathematics of quantum mechanics. It challenges our intuition, but also gives us tools to build technologies that were once science fiction. Quantum cryptography, for example, uses entanglement to create communication methods that cannot be hacked without detection. Quantum teleportation, another real phenomenon, has been demonstrated with photons over long distances, paving the way for future secure quantum networks. These are not vague mystical ideas, but concrete results supported by data. They are bizarre, yes, because they do not line up with how we normally experience the world. But bizarre does not mean unexplainable. Physicists spend decades developing experiments and mathematical frameworks to describe these effects with precision. The fact that they defy common sense does not make them supernatural, it simply means human intuition is limited. The universe is under no obligation to match our everyday expectations. So when people make mistakes about quantum mechanics, it's not a failure, it's a starting point. By correcting the misunderstanding, we can show that the real story is far more impressive than the myths. What quantum mechanics reveals is a universe filled with hidden connections, delicate balances, and rules that only reveal themselves when we look closely with the right tools. That is more inspiring than any simplified slogan because it is the truth. In the end, what matters most is clearing up the confusion. When scientists say observation, they are talking about instruments, detectors and measurable interactions, not about a person staring at something and changing it with their mind. The universe does not bend simply because we glance at it. Instead, it responds to physical processes that can be tested, repeated, and explained. Quantum mechanics can feel strange, but confusion should not be a barrier. In fact, it's a sign of curiosity, and curiosity is exactly what science thrives on. The more questions we ask, the closer we come to understanding the real mysteries of the quantum world. Don't fear the complexity, embrace it, explore it, and let it inspire. If you found this video helpful, make sure to like it and subscribe to our channel for more insights into science, reality, and the fascinating world of ideas.